In 4.9, our last objective for Unit 4, we're going to be sketching a curve using what we know about a function, its derivative, and its second derivative. So it's just one example. And I'm going to ask you to find all of its characteristics. So find all critical numbers, intervals where f is increasing or decreasing, and concave up and down, and find all the points of inflection. Then use this information to sketch. So the function we'll be working with is x over x squared plus 1. So talking about f first, what are some things we know about a rational function? When we're working with a rational function, we pay attention to things like asymptotes. So anywhere where the denominator would equal 0, no real value here would add to 1 to make 0. So there's no vertical asymptote. Any horizontal? Yes, it's bottom heavy. So there must be a horizontal asymptote of y equals 0, which there means there is no slant. As far as intercepts go, if I want an x-intercept, I let y be 0 and a fraction equals 0 only when the top does, so x equals 0. And a y-intercept would be if I let x equal 0. So I would get 0 over 1 is also 0. And that makes sense since that is the origin. Okay. So I have a few things that I can use already in my sketch. Now we'll move on to our first derivative test. We need to work on the first derivative here. And we'll use the quotient rule and simplify it. Alright, so working this out, we have x squared minus 2x squared is negative x squared. Alright, now for my first derivative test, we want to find critical numbers. Anywhere down here where the function doesn't exist, no, this is always going to be a positive number. Anywhere where the derivative is equal to 0 to find critical numbers, so set the top equal to 0, and we get 1 and negative 1. So first up, I have my critical numbers. Okay, then we're going to move on and do our first derivative number line test. We'll take all these values. We'll test our intervals here. Okay, plug those values back in and we get negative, positive, negative. So interpreting this for f, this is telling us that f is decreasing, then increasing, then decreasing. Interpreting that, we then have a relative minimum at negative 1, a relative maximum at positive 1. Since we are going to be sketching the function, we're going to go ahead and find the location of these points. So plugging negative 1 back into the original function there is going to give us negative 1/2. Plugging 1 back into the original function is going to give us 1/2. So these are actually going to give me some points to plot and more points to work with. Okay, we're going to go ahead and also write out those intervals where the function's increasing and decreasing. Here we go. And all of this is just going to help us make a nice sketch. So we need to move on and do our second derivative test to find out about concavity and possible points of inflection. So we're going to start from where we left off for our second derivative. And again, use the quotient rule. Alright, from here, we want to make sure we work this out nicely, so be really careful on the top. This is a big fraction here, and we're looking for something they have in common. They both have x squared plus 1, so I'm going to factor that out, and they both have a 2x, so I'll factor that out as well. Alright, that's going to leave me with a negative x squared plus 1. Over here, these two terms have been removed, so I'm left with minus 2 times 1 minus x squared. So I can do a little reducing here with the x squared plus 1 terms. 1 here and 1 here. Simplify what's left inside. And continue simplifying this. So 2x squared minus x squared is x squared, and negative 1 minus 2 is negative 3. So there's our cleaned up second derivative. I set it equal to 0. So anywhere where the top is equal to 0, that would be at 0 and plus or minus square root 3. So these are test values and possible points of inflection. We'll only know if they're points of inflection once we've done our second derivative number line test and we see a change in concavity at those values. Alright, so grabbing some numbers to plug in and test here. And plugging those numbers back into our second derivative. The denominator is always positive, so I won't worry about that. We'll just plug them into the numerator. So I get a negative times a positive is a negative. In the next region, a negative times a negative is a positive. When x is 1, a positive and a negative is a negative. And when x is 2, a positive times a positive is a positive. So it appears I do have a change in concavity at each one of those values, and they are all 3 points of inflection. If I want to find those values, I'm going to use my calculator to plug that in. I know this one's 0, 0. This is going to give me negative 0.4. This one down here will give me positive 0.4, so a little less than a half. Those aren't bad values. We can use those in our sketch as well. And then a little bit more here, we want to do our interpretation of our second derivative number line, which tells us where the function is concave, up or down. So down, up, and we'll write those intervals out as well. Okay, there we go. So now that we've found all of this, we're going to use all this information here to make a nice picture. Don't forget, you also have the information about the function itself with the asymptotes and intercepts. So we had no vertical asymptote, but we did have a horizontal asymptote, y equals 0. Okay. Now, if the number of vertical asymptotes also tells me the number of how many pieces my curve is, with no vertical asymptotes, there should be one more, so one piece. So our function is only made up of one piece. It is bounded somewhat by the horizontal asymptote. You'll also see there was an x and y intercept at 0, 0. So remember that it is okay to cross a horizontal asymptote if you have to, and apparently we have to because we have a point there. So we're going to plot some other points that we have found, -1, -1/2, and 1, 1/2. For my relative maximum and my relative minimum. Okay, and then I'm also going to go ahead and plug in my points of inflection. So 0, 0, I already have. -√3, -1/2. That's going to be about, well, not quite -1/2, -0.4 here. And then +√3, a little less than a half here. Okay, so those will be changes in concavity. So I have 5 points I can work with. I'll go ahead and draw through with pencil. My function is supposed to decrease from -infinity to -1. So here's the trick. Decrease from how high? So remember that there's a horizontal asymptote here, and you have no other x-intercepts here. So it can't cross it. So it's coming from way out here, just under the x-axis the whole time, decreasing. It's going to increase. This is the only place it's allowed to cross that x-axis, up here to my relative max, and then it should decrease the rest of the time. But again, there are no more x-intercepts, so our function is just going to follow that horizontal asymptote out. So filling in the concavity, we have concave down until -√3. So concave down here. Concave up until 0. So all the way concave up here. Okay, then we switch back to concave down, going all the way to √3. And lastly, concave up again, all the way out. So my function comes in this way, curves back. Okay, so there's my one continuous piece. Even though there were asymptotes involved, you were allowed to cross it because you were supposed to cross it. As long as you follow the information that you found from doing your first and second derivative tests, you should be fine, and your graph will come out correct.